Magnetic induction is a process where a voltage is induced in a conductor when it moves through a magnetic field. This induced voltage is directly proportional to the strength of the magnetic field, the speed of motion between the conductor and the field, and the number of turns in the conductor if it is part of a coil. Counter-electromotive force, often abbreviated as CEMF, is a voltage that opposes the change in current which causes it. When current flows in a conductor, it generates a magnetic field. If this magnetic field opposes the original magnetic field that caused the current flow, it's referred to as counter-electromotive force. CEMF is induced in the conductor as the magnetic field changes. Let's illustrate this with an example using a coil of wire and a magnet. Firstly, consider an initial state where the magnet is stationary and there is no induced voltage in the coil. Secondly, as the magnet moves towards the coil, it creates an expanding magnetic field. This expanding field cuts the conductors in the coil, inducing a voltage and causing current to flow. Thirdly, the current flowing in the coil creates its own magnetic field, and this magnetic field opposes the magnetic field of the magnet. This opposing magnetic field is what causes counter-electromotive force. Fourthly, when the magnet moves away from the coil, its magnetic field collapses. This collapsing field again cuts the conductors in the coil, inducing a voltage and causing a change in the direction of current flow. The counter-electromotive force in this case acts to prevent the current from flowing, opposing the change. There are a few key points to remember. Induced voltage and counter-electromotive force are both created by magnetic induction. Induced voltage is the initial voltage that causes the current flow, while counter-electromotive force is the opposing voltage created by the current flow. Counter-electromotive force is always in opposition to the original magnetic field that caused the current flow, a principle known as Lenz's law. The strength of the induced voltage and counter-electromotive force depends on the strength of the magnetic field, the speed of movement, and the number of turns in the conductor. In some simplified explanations, such as the one you mentioned from Delma's book, the process might be presented by assuming that the initial induced voltage is sufficiently strong to cause current flow immediately. This eliminates the need to explicitly mention the initial induced voltage. However, it's crucial to understand that the induced voltage always precedes the current flow and counter-electromotive force. To clarify further, let's break down the sequence of events when a magnet moves towards a coil of wire. Initially, the magnet is at rest relative to the coil, and there is no current flowing in the coil. As the magnet begins to move towards the coil, its magnetic field starts to interact with the coil's conductors. According to Faraday's law of electromagnetic induction, this changing magnetic field induces a voltage in the coil. This induced voltage is the electromotive force that drives the flow of current. Once the induced voltage is present, and if the circuit is complete, current begins to flow through the coil. This current is a direct consequence of the induced voltage. Now, as current flows through the coil, it generates its own magnetic field. This is a fundamental property of electromagnetism. The direction of this magnetic field is determined by the direction of the current flow, as described by the right-hand rule. Here is where Lenz's law comes into play. Lenz's law states that the direction of the induced current, and therefore the magnetic field it produces, will be such that it opposes the change that created it. In this case, the change is the increasing magnetic field due to the approaching magnet. So, the magnetic field produced by the coil's current will oppose the magnetic field of the approaching magnet. This opposition manifests as a force that tries to push the magnet away from the coil. This opposing magnetic field also induces a voltage in the coil that opposes the initially induced voltage. This opposing voltage is the counter-electromotive force, or CEMF. The counter-electromotive force acts to reduce the net voltage in the circuit, thereby limiting the current flow. It's a self-regulating mechanism that prevents the current from increasing indefinitely. The magnitude of the CEMF depends on the rate of change of the current and the inductance of the coil. A higher rate of change or a larger inductance will result in a larger counter-electromotive force. If the magnet's movement is reversed, and it starts to move away from the coil, the process is similar but with reversed polarities. The collapsing magnetic field induces a voltage in the opposite direction, causing current to flow in the opposite direction. The counter-electromotive force will still oppose the change, in this case trying to maintain the current flow in the original direction. Now, to address the confusion about whether there are two different voltages induced in the coil, the answer is both yes and no, depending on how you look at it. There is the initial induced voltage due to the changing magnetic field from the external magnet. This is the primary driving force for the current. Then there is the counter-electromotive force, which is also an induced voltage, but it's induced by the changing magnetic field created by the coil's own current. So, in a sense, there are two induced voltages, but the counter-electromotive force is a consequence of the first induced voltage. It's not an independent voltage source, but rather a reaction to the current flow caused by the initial induced voltage. The term self-induction refers to the phenomenon where a change in current in a coil induces a voltage in the same coil. This is precisely what happens with the counter-electromotive force. The coil's own magnetic field, created by its own current, induces a voltage in itself. This is why it's called self-induction. The counter-electromotive force is a direct result of the self-induction. Think of it like this: the approaching magnet induces a voltage. This voltage causes a current. This current creates its own magnetic field, and this magnetic field induces a counter-voltage. It's a chain reaction, but it all stems from the initial induced voltage. The Delmers book simplification focuses on the overall effect, which is that the induced current creates a magnetic field that opposes the original change. It doesn't explicitly break down the process into the initial induced voltage and the subsequent counter-electromotive force. But it's important to understand that both are present and play a role in the overall behavior of the circuit. Now, regarding the passage from Mike Holt's exam prep book, where it says that the varying electromagnetic field within the conductor causes the electrons in the conductor to move at 90 degrees to the flowing electrons within the conductor, this is related to the concept of self-inductance and the generation of counter-electromotive force. The expanding and collapsing electromagnetic field around the conductor, due to the change in current, induces a voltage in the conductor itself. This induced voltage opposes the original change in current, hence the term counter-electromotive force. The movement of electrons at 90 degrees is a simplified way to visualize the energy transfer and the creation of the opposing magnetic field. It's a consequence of the electromagnetic forces acting on the electrons within the conductor due to the changing magnetic field. The induced voltage always opposes the original change in current. This is a fundamental principle of Lenz's law. The counter-electromotive force is a manifestation of this principle. It acts to resist any change in the current flowing through the inductor. If the current is increasing, the counter-electromotive force will oppose the increase. If the current is decreasing, the counter-electromotive force will oppose the decrease. This opposition is what gives inductors their ability to store energy in the magnetic field. The energy is stored in overcoming the counter-electromotive force and establishing the magnetic field. When the current decreases, the magnetic field collapses, and the stored energy is released back into the circuit as the counter-electromotive force attempts to maintain the current flow. In summary, the induced voltage is the initial voltage generated when a conductor cuts through magnetic lines of flux. This voltage drives the current through the conductor. As the current flows, it generates its own magnetic field, which opposes the original magnetic field. This opposing magnetic field induces a counter-electromotive force, which opposes the original change in current. The counter-electromotive force is a self-regulating mechanism that prevents the current from increasing indefinitely. The strength of the induced voltage and counter-electromotive force depends on the strength of the magnetic field, the speed of movement, and the number of turns in the conductor. The Delmers book simplifies the process by assuming that the initial induced voltage is sufficiently strong to cause current flow immediately. This eliminates the need to explicitly mention the initial induced voltage. However, it is important to understand that the induced voltage always precedes the current flow and counter-electromotive force. To further elaborate on the concept of magnetic induction and counter-electromotive force, let's consider the factors that influence their magnitude. The magnitude of the induced voltage, often denoted as electromotive force, is determined by Faraday's law of electromagnetic induction. This law states that the induced electromotive force in any closed circuit is equal to the negative of the time rate of change of the magnetic flux through the circuit. Mathematically, this can be expressed as electromotive force equals negative n times the derivative of phi with respect to t, where electromotive force is the induced voltage, n is the number of turns in the coil, and derivative of phi with respect to t is the rate of change of magnetic flux. From this equation, we can see that there are three primary factors that affect the magnitude of the induced voltage. Firstly, the number of turns in the coil. A coil with more turns will experience a greater induced voltage for the same change in magnetic flux. This is because each turn of the coil contributes to the overall induced voltage. Secondly, the rate of change of magnetic flux. A faster change in magnetic flux will result in a larger induced voltage. This means that if the magnet is moving towards the coil at a higher speed, the induced voltage will be greater. Thirdly, the strength of the magnetic field. A stronger magnetic field will produce a larger change in magnetic flux, leading to a greater induced voltage. Now, let's consider the factors that influence the magnitude of the counter-electromotive force. The magnitude of the counter-electromotive force is determined by the inductance of the coil and the rate of change of current. The inductance of a coil is a measure of its ability to store energy in a magnetic field. It depends on the geometry of the coil, such as the number of turns, the area of the coil, and the permeability of the core material. The relationship between the counter-electromotive force, inductance, and rate of change of current is given by the equation counter-electromotive force equals negative L times the derivative of I with respect to t, where counter-electromotive force is the counter-electromotive force, L is the inductance of the coil, and derivative of I with respect to t is the rate of change of current. From this equation, we can see that there are two primary factors that affect the magnitude of the counter-electromotive force. Firstly, the inductance of the coil. A coil with a higher inductance will generate a larger counter-electromotive force for the same rate of change of current. Secondly, the rate of change of current. A faster change in current will result in a greater counter-electromotive force. This means that if the current is increasing or decreasing rapidly, the counter-electromotive force will be larger. The negative sign in the equation indicates that the counter-electromotive force opposes the change in current. It acts to resist any increase or decrease in the current flowing through the inductor. Now, to further clarify the relationship between induced voltage, current, and counter-electromotive force, let's consider a few practical examples. In a generator, a coil of wire is rotated within a magnetic field. As the coil rotates, it cuts through the magnetic lines of flux, inducing a voltage. This induced voltage causes current to flow through the external circuit, providing electrical power. The counter-electromotive force generated by the current in the coil opposes the rotation of the coil, requiring mechanical energy to be continuously supplied to keep the generator rotating. In a motor, current is passed through a coil of wire placed within a magnetic field. The interaction between the magnetic field and the current creates a force that causes the coil to rotate. As the coil rotates, it cuts through the magnetic lines of flux, inducing a voltage. This induced voltage opposes the applied voltage, reducing the current flow through the coil. The counter-electromotive force generated by the rotating coil limits the current and regulates the speed of the motor. In an inductor, a coil of wire is used to store energy in a magnetic field. When a voltage is applied to the inductor, current begins to flow through the coil. As the current increases, it generates a magnetic field, which induces a counter-electromotive force that opposes the applied voltage. The inductor continues to store energy in the magnetic field until the current reaches a steady state. When the applied voltage is removed, the magnetic field collapses, releasing the stored energy back into the circuit as the counter-electromotive force attempts to maintain the current flow. Understanding the concepts of magnetic induction, induced voltage, and counter-electromotive force is crucial for comprehending the behavior of various electrical and electronic devices. These principles are fundamental to the operation of generators, motors, transformers, inductors, and many other components. By grasping these concepts, you can gain a deeper understanding of how electrical energy is generated, stored, and utilized.